Since the dawn of mankind, fire has intrigued humans because of our need for warmth and light in times of darkness. Fires have also improved cooking and our overall health for much of our lives while living here on planet Earth. How else has fire improved our life? Correct? Correct. Correct. So yes, it has improved our life in cooking and cleaning, and it has overall given us a sense of warmth. It's given us warmth, so comfort in a way, right? And not just us, but it has provided a type of environment for plants to grow. Now, plants start off every single food chain. They start off every single food chain, and they are the givers of life in terms of they sustain life. Without plants, there'll be no us, because plants feed a variety of animals. They especially feed things that we like to eat, like chicken, and they also provide food for cattle. So all those big beasts that we like to eat, yeah, they actually eat a lot of grass. Sheep eat grass, goats eat grass. Yes, yes, so you get my gist. And so, with that being said, the energy travels along that chain. So if you get rid of plants, then there'll be no us. Additionally, plants are able to produce or be the primary producers in our food chain simply because they make their own food. This is catalyzed by the heat given off, by the light given off by the sun. Right? The sun is a big ball of fire, basically, and it produces light. Light is one of those things that come off of the sun. And so this light enters Earth's atmosphere and hits plants, and plants contain a green pigment called chlorophyll. This chlorophyll becomes activated by the light, and it utilizes two reactants. Firstly, it utilizes carbon dioxide and also the water that the plant takes in. The carbon dioxide enters the plant through something called stomata, which is found on the underside of the leaf, right? And so when these two molecules meet together, they marry, and they become catalyzed. So light is like the priest that's marrying these two molecules. And what comes off, the products that come off, are vital because, number one, glucose is produced. That is what plants produce to keep themselves going. And the second product is oxygen. Oxygen is given off into the atmosphere for us. So it's like a recycler of air. It recycles air and makes life better for us. And here we have the final drawing of that little cartoon that I gave you just a while ago. Lovely, isn't it? Now, in the study of heat, there was a theory called caloric theory, and it became obsolete. It was a theory formulated in the 18th century. People used to want to study heat. They wanted to understand how heat works and how the things get heated up, and so they made this theory. And what they thought was that heat was this invisible fluid called caloric that used to enter substances to cause them to heat up. But it was not, because what they found were four main things. This is why the caloric theory is obsolete at this point. 1. Heated bodies did not increase in calorie during phase changes. Example, solid to liquid or liquid to solid. So there was no temperature change there. Different substances experience different amounts of temperature increases when given the same amount of heat. And when a body, this was the most important one, and this is what I tested to show the students that caloric couldn't exist, was that when a body or object was heated, it did not increase in weight. The weight remained the same. And so what I did is heat up a metal. I took the mass of it first, just to let the kids see, the students see, and everybody was involved. Everybody We're involved in this whole process. We took the mass and we used a top pan balance. Well, actually no, we used triple beam balance because our top pan balance is a bit sensitive. So that's what we did. And did we? Oh no, we didn't. We used a spring balance. Yeah, we used a spring balance because it could hang off of that. So we set up a retard stand and we put the spring balance on it and we hung the mass on that spring balance. We took the mass before, then we put we put some water in a beaker and set up the tripod stand with Bunsen burner and everything, and we put the mass in there while it was on top of the spring balance. We didn't even have to move anything from the spring balance setup. And then when we had heated it enough and we tested the heat of the water, which was about 99 degrees Celsius or something like that, and we removed the water, we saw that the mass of the metal was still the same, which says that caloric couldn't be an invisible fluid, because then it would have some sort of mass to cause a change in mass of that metal, right? And so that is another reason why the caloric was not true. So it had to be obsolete, made obsolete. And then finally, another famous scientist known as Rumford, he used his cannon boring experiment to prove that when work was done on the cannon by boring, the boat heated up. So again, if I am touching you and I'm warming you up, right? Suppose I'm hugging you. My heat is supposed to make you warmer, yes, but then if it's an invisible fluid that's leaving my body to enter your body, what do you think will happen? I'm supposed to cool down. But that does not happen. If I am hugging you, guess what's happening? We're both going to come to equilibrium. We're both going to end up being the same heat, or same temperature, sorry. We're both going to turn out giving up the same temperature because of equilibrium. The heat is going to equilibrate. So, that is why the caloric theory is now presently obsolete. But we have to give credit to these people, because otherwise we'd be thinking this thing still was an invisible fluid that entered bodies. But we have to remember that this was the Dark Ages. And in the Dark Ages, many things were believed and practiced that we actually gawk and laugh at today. For example, bloodletting. Our veins were cut open, our leeches were used to get rid of bad blood during times of sickness. Imagine you're sick and people cut open your hand to bleed you out to get rid of the bad blood, the same blood that you need to help you get better. Then they had something called trepanation, which was the boring of holes into the skull. Wow. Now, do note that temperature is a measurement of heat. Temperature is a measurement of heat. Now, temperature of a body can be measured in degrees on the Celsius scale, named after the Swedish scientist Anders Celsius, who suggested it. Temperature can also be measured on a Kelvin scale, which was devised by Sir William Thomson Kelvin. The temperature of a body tells us how hot it is. A temperature scale is a simple way of expressing the relative hotness and coldness of objects. Hotter objects will have higher temperature. There's several scales, several temperature scales, such as what we mentioned before. We have the Kelvin scale, we have the degree Celsius scale, and we also have the Fahrenheit scale. Now, of these three, we like to use Celsius because Celsius is more relative to us. If you say that something is 0 degrees Celsius, we know it's cold. It's relative, right? If you say something is 100 degrees Celsius, we know it's hot because it's relative, right? But if you say something is 32 degrees Fahrenheit, you can't really relate because you relate 32. What is that? Right? So we stick with the Celsius scale because, I mean, we could relate to it easier. The Celsius scale is based on the properties of water. And again, we are always messing with water. We drink water, we live off of water, we cook with water. So that's why we use the Celsius scale to relate to most temperature changes. right? We know, now you know that the freezing point of pure water is 0 degrees Celsius, and the boiling point of pure water would be 100 degrees Celsius. And in this picture we have the relationships between all different temperature scales, where you have 30 degrees Fahrenheit being related to 0 degrees Celsius being related to 273 Kelvin. So all of them represent 0 degrees Celsius. Then we have here at 100 degrees Celsius, we see that 212 degrees Fahrenheit is related to 100 degrees Celsius, whereas 373 kelvins is related to 100 degrees Celsius. Which scale would you prefer? You make your pick. I know I like the middle scale the best. Now the Kelvin scale is based on the properties of ideal gases and the energy of particles. The low point of the scale is referred to as absolute zero. That is where nothing happens. Nothing. It's just, there is nothing. Right? So at absolute temperature, the particles have zero thermal energy, meaning there is no heat whatsoever. And so they cannot become any colder. At this present time, can't come any colder. Now, of course, you know, physics is like the Trojan horse that we use to introduce math. And you're going to have to learn how to convert between Kelvin and degrees Celsius and degrees Celsius and Kelvin. So let's just look at it. So if you want to convert between Kelvins to degrees Celsius, you have to subtract 273. If you want to, so if I write it here, let me just write it here. So to go from Kelvin, this is an easy way to remember it, to degrees Celsius, we subtract 273. And to go from degrees Celsius to Kelvin, it's just as simple. You just add 273 as our things show here. So if you have 293 kelvins and you want to go to degrees Celsius, you just subtract 273 to get 25 degrees Celsius. And to convert from degrees, to go from 30 degrees Celsius to kelvins, you simply add 273 and you get 303 kelvins. Here we have a little exercise. So that have been worked out for you already, where you have 0 minus, so you could actually try to work these out by yourselves. So you have 0 minus 273 equal to negative 273. 77 minus 273 equals to negative 196. Negative 117 plus 273 is equal to 156. So if you'd like, you could actually try to work these out on your own if you drop a table and try them out on your own. Then here we have how to convert from degrees Celsius to degrees Fahrenheit and from degrees Fahrenheit to degrees Celsius. And it's pretty simple if you look at it here. It's pretty simple. So to go from degrees Celsius to Fahrenheit, you just multiply 1.8 by degrees Celsius by whatever you have for degrees Celsius, and then you add 32. And to get degrees Celsius, to convert from degrees Fahrenheit to Celsius, you simply just subtract 32 from the degrees Fahrenheit and divide by 1.8. And here it has been done for you as well. So if you wanted to go from 0 degrees Celsius, you would use, to Fahrenheit, you would use equation 1, which is right up here. And if you look at it, you will see you have 1.8 times 0 will give you 0 plus 32, which would eventually give you 32 degrees Fahrenheit. So 0 degrees Celsius is equivalent to 32 degrees Fahrenheit. 32 degrees Fahrenheit is equivalent to 0 degrees Fahrenheit. And that makes a lot of sense because this is just the reverse of this. Then you have 100 degrees Celsius, which is equivalent to 212 degrees Fahrenheit. So again, if you're solving for Fahrenheit, you go to the Fahrenheit equation and you stick in whatever is degrees Celsius in there. And then for the negative 5 degrees, you would use the second equation, where you get negative 20.6 degrees Celsius, which is equivalent to negative 21 degrees Celsius. Okay? Now, what heat energy is basically thermal energy is heat energy. Thermal is just another word for heat, and it is measured in joules. Heat is transferred from a hotter body to a colder body. Heat is transferred from a hotter body to a colder one because the average kinetic energy or speed of the molecules in a hot body falls as a result of collisions with the molecules of the cold body. When the average kinetic energy of the molecules is the same in each body, they are at the same temperature, which is referred to as the thermal equilibrium. So this is what I was saying earlier, right? So whereas temperature is a measurement of heat, heat is the energy required to do what? Right, so heat gives atoms energy, basically energy for them to vibrate, right? It is the energy that is applied to substances to cause vibration in atoms, and this is how heat is transmitted into conductors, right? That's how it's transmitted through conductors, and also other various materials, but more so in conductors such as metals. So next up, in our next episode, we're going to deal with thermometers and the different types that exist and why they're used and stuff like that. So see you around for section 2 or episode 2. Alright, bye now.